Alright, any pilots, I hope you are doing absolutely fine. And this will be the last lecture on aircraft systems. So, if you're watching this, thanks for following the series. And, guys, one more thing, since this will be the last lecture, and there is still a lot to cover in technical general, which includes your principle of flight, you have your electrics, engines, right? So, all of those things will be covered in the live classes. Alright, so you guys can join the live classes. It will be on Zoom, right? So in order to join the classes, you have to fill a form, right? So the form links are in the description. You can just click the link in the description, or you can go to the comments. Just click on this link, and then you will be directed to a form which you'll have to just fill up. It's a very quick form, so just fill it up, and then we'll talk. All right. So let's start with our last lectures on aircraft systems, which is fuel systems. All right, so let's start with fuel systems. All right, so firstly, we have ideal fuel qualities. So what are the ideal qualities of a fuel? So first thing first, the fuel should be easy to flow. Obviously, it has to flow through a lot of pipelines, a lot of motors, so it should be easy to flow. Secondly, it should have a complete combustion and no residue, right? So it should be combusted completely. Unlike if you have, for example, wood and you are burning wood as fuel, then what will happen? The wood will leave coal as residue, right? So coal will be left out, right? So a fuel is considered to be a good fuel if there is no residue at the end, like your LPG that you use in your house, right? So it does not have any residue, right? So that is a very basic thing. I just wanted to explain a little. So yeah, so it should have a complete combustion and no residue. The third thing is that it should have a high calorific values. What is a high calorific value? So it is the amount of heat released during combustion, right? So some substance release a lot of heat when they are burnt. So they are having what? High calorific value. And a fuel is considered to be a good fuel if it is having a high calorific value. The one, two, three, fourth thing is it should be non-corrosive. Makes a lot of sense. Then there should be no fire hazard. All right. Last thing is that it should be a good lubricant, right? So it should have a good lubrication quality, obviously. If it is a good lubricant, much easier functioning, less frictional losses. All right. So none of the fuels that we have today have all of these properties. Obviously, there is no one ideal in the world, no one is perfect. So we don't have any of the fuel that contains all of these properties. Some will be there, some will not be there. All right. Next thing we have is our first type of fuel. So firstly we have aviation gasoline. So this is the first type of fuel that we have to study. Alright, so aviation gasoline is a type of fuel which is more commonly known as AVGAS. Alright, so you'll hear this name a lot. This is aviation gasoline. Alright, so AVGAS, it is how it is commonly known as. And the second point is that AVGAS is used by piston engine aircraft. Alright, so AVGAS will be used in what? Your piston engine aircraft, like the ones you'll be flying during your training. Right. And the third is that AVGAS is rated by octane rating. So what is octane rating? So octane rating is a measure of the fuel's resistance to detonation when it is subjected to high pressure and temperature. Right, so octane rating is something you'll be studying in piston engines, right? So just because I did not want to leave anything, I'll just explain it in quick. So octane rating would be the resistance to detonation, right? So what is detonation? See what happens if this is a cylinder and this is a piston, right? So how does a piston engine work? It has like a variety of cycles, right, in which what happens majorly is the piston moves up and down the cylinder, all right, and the mixture here is of fuel and air, and this thing get compressed, right? As the piston moves down, this thing get compressed, right? The piston will be here, so this thing get more compressed. If the piston is here, this thing will get a lot more compressed, and there is a spark plug here, right? So there will be a spark plug at this part of the cylinder, and the spark will plug will produce a spark, and as the spark is there, then this fuel and air mixture will start to combust, and as it combusts, the piston will move upwards very rapidly. So this is how the piston engine works like in a very brief manner, right? So what happens is sometimes what could happen is during your compression stroke when you are making this piston go down, in that stroke what will happen is the fuel and air mixture that is here becomes so much compressed that it heats up a lot, and without the spark plug producing the spark, right? This spark plug used to produce a spark and then only it used to like go up, right? But in this case, in case of a detonation, what happens is the spark plug do not produce the spark, but just because of the heat produced due to the compression of the piston engine, due to the compression of this mixture, there is so much heat present that without the need of ignition, it automatically starts to go upwards and the power stroke starts to happen, right? So this is known as detonation, right? So this is when your ignition, sorry, your cycle is disrupted because the ignition was supposed to happen when the piston has moved completely downwards, but as the piston moved only this much down, the ignition or the power stroke already happened because of so much pressure and temperature in this part of the mixture, right? So if you didn't understand it, no worries. You will be studying it in piston engine, right? So that is why I'm telling you to join the live classes. There will be covering these all topics, right? But if you didn't understand it, no worries for now. Octane rating is the measure of the fuel's resistance to detonation, right? So how much of fuel air mixture can you compress? Like what is the maximum limit till which you can compress this thing, till which there is not that much heat that it will detonate or it will start the power stroke without the spark plug, right? So this is your octane rating, right? Nothing to worry about if you do not understand it at this stage. All right, so there is a little more about octane rating. So first point is octane rating is measured using a test engine, right? So a test engine is used to find out the octane rating of a particular fuel type, right? And how is it used? So keeping the mixture weak, right? It will give us a low octane number. So there are two octane numbers. We have a low octane number and a high octane number, right? So how are they find? So we use a test engine, and in a test engine, we firstly keep the mixture as weak. And when the mixture is weak, we get a low octane number, all right? And the next thing we do is when we keep the mixture as rich, we get a high octane number. So we get our low and high octane number with the help of a test engine by keeping our mixture weak and lean, weak and rich. All right. And then what did we do by getting these two numbers, by getting high and low octane numbers? So it's just something that gives us a performance index. What is a performance index or a performance number? It is equals to the low octane number slash your high octane number. So using a test engine, we find out the low octane number and a high octane number. And with the help of these numbers, we have defined a performance index for any kind of fuel. Performance index is your low octane number slash your high octane number. So for example, if a fuel is having a low octane number of let's say 100 and a high octane number of let's say 130, so we can write the performance index as 100 slash 130, right? And the lower octane number is written with the fuel name, for example avgas 100, right? So this is actually a fuel type which is used in a lot of piston engine aircraft, which is what avgas 100, right? So if someone asks you what is the full form and what is the meaning of avgas 100, so you can confidently explain them that AVGAS means aviation gasoline. 100 here means the octane rating. And if you understood the octane rating part, then you would know what a octane rating is, right? So this is your octane rating. Now, your aviation gasoline type of fuel is available in three parts or three types, right? So what are these three types? So we have aviation gasoline 100 as we just saw, and the color that you need to remember is very important for your exams, right? So aviation gasoline 100, which is your avgas 100, is of green color. All right, so here you can see the image also that avgas 100 is of green color. and your AVGAS 100 LL. So it is also AVGAS and it is also having an octane rating of 100. The LL here means low lead, right? So it has a low lead content. That is why it is written as LL. Alright, so its color is what? Blue. Only the colors are very very important here. Alright, so AVGAS 100 is of green color, AVGAS 100 LL is of blue color, the image is here, and your MOGAS is of clear color. It does not have any color. So MOGAS is also a type of fuel. Alright, so just remember these colors, they are important for your exams. Now, the next type of fuel that we'll be studying is our gas turbine engines fuel or jet engines fuel, which is known as jet alpha 1. So this is your jet alpha 1, and as the name itself contains jet, so it will be used in your jet engine aircraft. And if you don't know what a jet engine is, again, I'll be promoting my links again. But guys, in the description there is a link in which you can join the classes, and there will be covering what jet engine is. All right. So yeah, back to the class. Right. So jet engine and like in our piston engine, we used what? Avgas, right? Aviation gasoline. But similarly for our jet engine, we use what? Jet. Oh, sorry. Oh, oops. Jet Jet Alpha 1. Right, so Jet Alpha 1 will be used in your jet engine, and it is very easy to remember, right? Avgas for your piston engine, Jet Alpha 1 for your jet engines, right? And jet engines are also known as your gas turbine engines, so don't get confused between the two. Right, now what is written here? The gas turbine engine or the jet engine uses jet alpha 1. All right, we know that. And yeah, this is again very important. The colors, DGCA loves these kind of question. Jet alpha 1 color is clear or straw yellow, as some people like to call it. All right, remember the color again. I'm telling you, very very important for your exams. Now there is something known as a cloudy fuel. So what happens is there might be a cloud in the fuel, right? So if yeah, not an actual cloud, guys, obviously, right? So what happens if the fuel sample is swirled vigorously, if you like stir it vigorously, right, with the help of something, and the sample starts to appear cloudy, this means that the fuel is contaminated, right? So if you take a sample and stir it or just move around the beaker very, very fast, then if you see clouds in the sample, which means that your fuel sample is contaminated, right? And one more thing, if the cloud rapidly moves upward, if this cloud starts to move upward, which means what? There is air present in the fuel. Obviously, the air is lighter, so it will move upwards and try to escape from here. But if this cloud sample rapidly moves downwards, the water is present, right? So in this sample, you see the cloud as starts to move downward, which means what? There is water in the fuel. So the fuel can be contaminated with air if the cloud is moving upward. And if you see the cloud is moving downwards, which means the fuel is contaminated with water. Right, so next is FSSI. What is FSSI? So you'll be shocked to know that all of the different fuel that we use, they all have a little bit of water inside of them. Yes, all of the fuels that we are using, they have a little bit of water in them, right? So a small amount of water is present in all the types of fuel. So what happens is this water can freeze at high altitude and block the filters, right? So at higher altitude, as you know, the aircraft fly at higher, very, very high altitudes, right? So the water can start to freeze because the temperatures are very, very low. So this water, they can now be crystals, right? So these crystals, when they're used, right, they can go into your filters. You know, there'll be filters to clean the fuel before you put in the engines, right? So these filters can get blocked because of the ice crystals, right? So this is an issue, right? So you don't want ice crystal in your fuel, but you cannot separate complete water out of your fuel because it is there in all the different types of fuel, right? So a small amount of water is there and the ice crystal can block. So what do? You add FSSI. Hence FSSI, or the full form is fuel system icing inhibitors, right? So you add fuel system icing inhibitors to the fuel, and what they do, they prevent the water from freezing. Yes, that is exactly what we want, right? So they freeze the, they prevent the water from freezing, which, and also the second purpose is that they avoid the fungus growth in the fuel. Again, if there is any fungus growth in the fuel, they can also jam our filters, right? So they does two purpose. They don't allow the water to freeze, and also they don't let any fungus to grow. Right. So this is your fuel system icing inhibitors. All right. Alright, so next is water contamination in fuel tanks. Right, so what happens is your fuel tanks are generally filled till top to avoid any air inside the fuel tank. Why? See, there is our fuel tank here, right? It's a wing of an aircraft, it is an aerofoil, right? So the fuel is filled in the aircraft like this. As you can see, this is the fuel, but there is a little gap over here in which there is some air, right? So why is it then dangerous, and why don't we want any air in the fuel? So what happens is this is atmospheric air, right? So this might contain a little bit of moisture in it, right? And this air, if it contains moisture in it, then what will happen? It can contaminate the fuel, right? At higher altitudes, the air can condense and the water can just enter the fuel, right? So that is why you don't want any water, or sorry, any air in the your fuel tanks, right? So what do you do? Since this air might contain some moisture, it may contaminate the fuel, right? As I already explained. So what do? You fill up the tanks till full, right? You completely fill the tanks so that there is no space left for air. But what happens if you fill the tank completely? So if the ambient temperature changes, right? If the ambient temperature, for example, there was cold outside, and when the fuel tanks were filled, and in the morning there was heat, there was sun, so there was heat outside. Now this heat will cause what? It will heat up the fuel inside the tanks, right? And this fuel, when it will get heated up, it will expand, right? Anything when you heat up, it will expand, so the fuel will start to expand. And since there is no room for the fuel to expand because we filled the tank completely, right? So this fuel will start to leak, right? So this fuel will start to leak, and this is embarrassing, right? So, but this can cause the tanks to overflow if the ambient temperature increases, since the fuel will expand, right? As I explained. So this is an issue that you should be aware of. Next is fuel cooled oil cooler, right? So as the name is a little weird, but the function is pretty cool. See, what happens is even though the FSII, what is the full form of FSII? Fuel System Icing Inhibitors. All right. So even though we add FSII, why we add it? Because we don't want the water inside the fuel to freeze, right? So even though this thing is added in the fuel is heated before using it, right? We don't trust on just one FSI thing, right? So there are always backups and secondary systems assisting, right? So that is how this air travel is made so safe, right? So even though we add FSII, we still heat the fuel before using it, just in case there is any bits of ice crystal still remaining. So we heat the fuel before using it. How do we heat it? We can either use our compressor's hot bleed air, or a cooler way is to use a fuel cooled oil cooler. Right. So what is a fuel cooled oil cooler? This is done by using a fuel cooled oil cooler. So what is a fuel cooled oil cooler? So these kind of coolers, they use hot engine oil to heat the fuel, right? They use the engine oil instead of bleed air, right? You can use bleed air in some aircraft, it is like that. But if you are using this thing, which is the fuel cooled oil cooler, so what it does, it uses hot engine oil, right? So it uses hot engine oil to heat the fuel, which in returns cools the engine oil, right? So engine oil, it is hot and it needs to be cooled down for it to function properly, right? So this hot engine oil enters the chamber, and where your fuel is there, right? So the fuel is getting warmed because of the oil, and the oil is getting cooled because of the fuel. So they both are helping each other in in attaining the temperature they want, right? So the oil is getting cooled, right? Oil is getting cooled and the fuel is getting heated up. Mind my writing, but yeah, this is your fuel cool oil cooler. All right. Next is fuel waxing. So what is the fuel waxing? At very low temperatures, the hydrocarbon in the fuel starts to form crystals which can clog the filter known as fuel waxing, right? So this is not fuel freezing. Fuel freezing, we saw that there was some water molecules that was in the fuel which were freezing. So that was fuel freezing, right? But fuel waxing is a little different. Actually, it is freezing of hydrocarbons, right? So when hydrocarbons inside the fuel, there are hydrocarbons in the fuel like C and H bonds. There are methane, ethane. I'm not that good at chemistry, but yeah, there are hydrocarbons in the fuel. And these hydrocarbons, when they freeze, they can clog the filter, and which is known as fuel waxing, right? So this happens at a very, very low temperature, right? So it won't happen at a normal, a low temperature. So this is a problem with aircrafts that are flying in a very, very cold environment, right? So this is what fuel waxing is, and these kind of crystal will be formed inside the fuel, and these are not water crystal. Again, these are your hydrocarbon crystals, right? And I have mentioned it here too that it is different from fuel freezing since hydrocarbons are converting into crystals and not the water inside the fuel, all right? And the next thing is fuel boiling, right? So this is opposite to fuel waxing. So the temperature at which any liquid boils reduces as the pressure on its surface reduces, right? So this thing is from your lecture number one, right? If you have watched that, then you might know it. It is from a very early lecture, and even in the last lecture, we need it. So that's why I was telling you to watch the playlist video by video. All right. So I'll anyway explain it again. Right. So there are two ways to boil any liquid, right? So method one is by heating, right? So you have your water, for example, here in the beaker, and you are heating it with flame, right? So this is method one, which is very, very basic and we all know it, right? And there is a method two of boiling a liquid, which is not by using heat, right? What we can do is we can reduce the atmospheric pressure that is above this surface, right? We can reduce the atmospheric pressure that this liquid is feeling, and more accurately I can draw it like this liquid is feeling atmospheric pressure, right? Even in this case it is feeling atmospheric pressure, right? Even we as human beings are feeling atmospheric pressure, right? So what happens as this is pure water, so it will boil at what, 100 degrees Celsius, right? But if we reduce this atmospheric pressure, for example, in second case, I reduce the atmospheric pressure. So what will happen? The water will start to boil at, let's say, around 15 degrees Celsius, right? So the boiling point has reduced because I have reduced the atmospheric pressure, right? So atmospheric pressure is a reason why water is in liquid state, right? And so you know the two methods of boiling any liquid. Firstly, we can increase the temperature, right, as known as boiling, very common. The second method is by reducing the atmospheric pressure, right? So what happens is our aircrafts, they fly at very, very high altitudes, right? And as the altitude increases, we all know that the pressure reduces, right? So at Earth's surface, there will be a lot of atmospheric pressure, right? The pressure is very, very high here, and the pressure is very low at higher altitudes, right? So what will happen is the fuel, in our case, the fuel was boiling at, let's say, 100 degrees Celsius here, but as I told you that as the as the pressure reduces, the boiling point of the fluid will also reduce, right? So the fuel at this altitude, since the atmospheric pressure is low, will boil at, let's say, around 15 degrees Celsius, right? So the problem of boiling will be very easily triggered at this altitude, right? Because the fuel is boiling at a lower temperature, right? So this is an issue with our fueling system, that the fuel can start to boil. And what is the issue with fuel boiling? So again, from initial chapters, we have seen that as the fuel boils, it will develop what? Liquid vapor. It will convert into vapor form, which will cause what? Bubbling, right? So these bubbles will then disrupt the flow of this liquid or our fuel into the engine. So there will be something known as vapor lock, right? And let's read this. The aircraft climb, as the aircraft climb, the pressure reduces, right? And hence the fuel starts to boil at a lower temperature, as we just saw, right? The suction created by the pumps sucking the fuel reduces the pressure further, right? So I'll explain this part too. What happens? Already there was fuel boiling at a lower temperature, right? As the because our atmospheric pressure was low here, right? But one more thing that happens is that the fuel won't be just directly going into the engine magically, like it won't be teleporting, right? So we'll have to suck the fuel from the fuel tanks and supply it to the engines, right? So these are your engines, right? So you'll have to take the fuel out of the pumps, so out of your tanks and supply it to the engine, right? So in order to do that, you'll have to add a pump, right? So you'll add a pump here, and this pump will do what? It will create a suction, right? It will suck in the fuel and it will throw it to the engine, right? So this suction created by the pump will also reduce the pressure over here. It will reduce the pressure on the surface of your fluid or your on your fuel, right? So the pressure will be further reduced, right? Already our aircraft was at this high altitude and the atmospheric pressure was this low, which caused our boiling point to reduce. And on top of that, you have reduced the pressure further by creating this suction pressure, right? So I hope you're able to connect the dots and how interesting it gets, right? So this all has caused what? The boiling point to further reduce. So for example, the fuel will now boil at like literally 5 degrees Celsius, right? And it was boiling at what? 100 degrees Celsius when it was on ground, and now see in the air it is boiling at what? 5 degrees Celsius. So it is very easy to attain 5 degrees Celsius, right? Obviously the temperatures are very low, so 5 degrees is nothing. It can be very easily attained, right? So the fuel can start to boil, right? Now this boiling fuel will start to create bubbles which will disturb the flow of the fluid and or of our fuel into the engine, right? So this creates bubble in the fuel which can disturb the flow of fuel in the engine, as known as your vapor lock. So this is known as something vapor lock, right? So because of the bubbles, the flow is disturbed and this is vapor logging. I know I have explained it a little too much, but uh, I hope you found it interesting, right? Next, to solve the problem of fuel boiling, booster pumps are installed, right? So to avoid this from happening, to avoid vapor locking, we install something known as booster pumps. So in this diagram, you can see that we have a booster pump. So booster pumps that pressurize the fuel and hence pushing the fuel towards the engine rather than the pump sucking the fuel from the tanks, right? So earlier what we had, our tank and the pipelines were sucking the fuel with the help of a pump and it was going to our engines, right? But this was creating what? Lower pressure in our tanks, which caused our fuel to boil, right? So what we did, we added another pump and we connected it with our fuel tanks like this, and we called it what? Booster pump. So booster pump, it pressurized your tanks or your fuel tanks so that this pump don't have to suck in, right? So it would reduce the pressure for the rate. That is why we have added a booster pump. This will create additional pressure on the fuel. So this fuel will now flow towards the engine without creating a suction pressure, right? So this is known as a booster pump. In this diagram also you can see this is a booster pump, and your fuels will be located in your wing. If you know your aircraft, the fuel will be contained in the wings. As this is your booster pump, and this booster pump will pressurize the fuel towards the engine. As you can see in this case, it is shown connected to the engine, right? So this is your booster pump. and these booster pumps are submerged into feeder box. Very, very important, feeder box. So what is feeder box? It feeds the booster pump at all running condition, hence preventing starvation, and also allows for cooling. Right. So your booster pumps, as you saw, your booster pumps are submerged into fuel. So there is a box like this, and you have your fuel in this box like this. There is fuel in the box, and the feeder or your booster pump is submerged into this fuel. All right, so this is known as a feeder box. It's nothing, it's just a box in which you submerge your booster pump so that the booster pump never runs out of fuel, and hence cutting the supply, right? So this is known as a feeder box. Then there is a concept of specific gravity. So what is a specific gravity? Specific gravity is the weight of the liquid divided by the weight of water. So you are comparing it with water. You are comparing any liquid with water. In this case, we will be comparing our fuel with water. All right. So in this diagram, you can understand the concept very easily. See, we have 1 gallon of fuel in this beaker. All right. Remember the volume, it is 1 gallon. In the second case, we have again 1 gallon of water, right? So both of the volumes are same, right? But one is fuel, another one is water. Now we go and we measure it on a weighing scale, right? We put both of the beaker on a weighing scale. First weighing scale shows that the fuel weighs 8 pounds and the water is weighing 10 pounds, right? Although the volume is same, but the weights are different. So obviously because the densities will be different, right? So now, to find the specific gravity, you have done is what? You have taken the weight of the liquid, in this case, the weight of the fuel, which is 8 pounds, and we have divided it by our weight of water. So, what is weight of water in this case? It is 10, right? So, this gave us what? 0.8. So, this is your specific gravity, right? So, now you might have understood it very easily, right? So, specific gravity is inversely proportional, it should be inversely, right? So it is inversely proportional to temperature. This usually does not make much difference in large modern aircraft, all right? So this is a thing that you can keep in your head, right? A specific gravity is inversely proportional to your temperature, all right? Now there is something known as baffles. If you remember from the hydraulic series that we studied about baffles, baffles were helping to prevent the surging and slushing of fuel during maneuvers. That is exactly what they are doing in here, right? So baffles are installed in your wings also. In that case, we saw that baffles were in our hydraulic reservoirs, right? So they were also doing the same thing. Here also they are doing the same thing. They are installed in our wings, right? So we have baffles in our wings. They prevent what? Large inertial movement generated during the maneuvers, right? So during the maneuvers, the fuel might move here and there, right? And there's a lot of fuel, so it can create large inertial movements, right? It can move the aircraft around, right? So that is why we add baffles. So they are fitted in the fuel tanks to avoid large inertial movements generated during the maneuvers, all right? Then we're going to study about the large aircraft fuel system, right? So large aircraft use integral fuel tanks, right? What are integral fuel tanks? So it is just aircraft components or aircraft structure itself is being used as fuel tanks, right? So here you can see that the wings, although they are wings, right, they are necessary for the aircraft, but to provide a lift obviously, but they're used as a fuel tank too, right? So this is saving space, this is saving your cost of production and also a lot of weight, right? So the integral fuel tanks are using your aircraft components as fuel tanks, right? So what are these fuel tanks? So we have our left wing tank. So this one would be our left wing tank. We have a right wing tank. So this wing will be having a right wing tank. We have a center tank. So this portion, this is also a portion of the wing. So this is as the center wing tank, and then you have a stabilizer fuel tank. So we have a fuel tank in the stabilizer too, right? And one very, very important thing that the fuel can be transferred between the tanks to adjust the center of gravity, right? So you can transfer the fuel, for example, your wing or your center tank to your tail. So what will it do? It will transfer the center of gravity from, for example, here to the rear section, right? Because you're moving the weight around the aircraft, right? So the CG can be moved around with the help of transferring fuel between the tanks. Now there is a vent system which is used in these kind of fuel systems used by modern large aircraft. What is a vent system? So ram air can be used to partially pressurize the tank mid-flight, right? So we saw that it would be great if we pressurize the tank, because if we are sucking out the fuel through the tank with the help of pumps, then we saw that what it causes, right? And transferring it to the engines, then you know what happens, we suck in, and what happens, the pressure reduces further, and this reduction in pressure caused what, fuel to boil, and this fuel boiling will cause vapor logging, right? It will disrupt the flow. So this was the problem. So what we did, we just connected a simple pipe like a vent. We have connected all of the different tanks, like for example left, center, and your right wing tank. We have connected it with a vent pipe, right? All of these tanks will have a common pipe, and this pipe is going outwards, and it is connected with ram air, right? So they are directly exposed to ram air from earlier chapters again. So there will be flowing air coming from here, right, due to aircraft motion known as ram air, right? So all of this air will be coming in. This air will be entering the vent system, and it will pressurize your what do you call it, fuel tanks, right? So there will be some positive pressure at least, which will allow the fuel to flow to the engines, right? So this is what a vent system is. This will increase the pressure over the fuel surface, reducing the chances of fuel to boil, obviously, right? The fuel won't boil if the pressure is there, right? And the vapor lock, it prevents vapor lock, right? Next, there is a cross-feed valve. So what is a cross-feed valve? A cross-feed valve allows the fuel to be fed from any tank to any engine, right? So you have your left engine, you have your right engine, and they are having their own fuel tanks, right? So this is tank for left, this is tank for right. Now you can transfer the fuel from tank left to tank right, or from tank left to directly your right engine, right? So usually left tank will be for left engine, right tank will be giving fuel to the right engine. But by operating a cross feed well, this that you're seeing is a cross feed well. So if you operate this well, then you can transfer the fuel from left tank to your right engine, or from right engine to your left engine, or you can transfer the fuel between the engines, right? So all of these things are done with the help of a cross feed valve, right? Remember this thing, again, important. Then there is a sequence of fuel usage, right? So don't randomly use fuel in whichever tank you want to. There is a sequence. So the aircraft fuel tank is divided into outer, inner and outer section, right? So in this diagram, you can see that this is your inner portion of the tank, right? And this is again inner portion for your right fuel tank, right? So these are your inner portion, right? And then there is a outer portion of the tanks. So there will be, this would be considered as your outer portion. This is your outer portion, right? So what do you do? First of all, this is your inner and outer, and this will be your, what do you call it, your center tank, right? So as we already saw that the three tanks were there, inner your center tank, your left tank, and your right tank. So the wing tanks are divided further into two sections. You have your inner and outer, and on this also you have your inner and outer. All right. So why is it done? It is done so that you can use your inner tank fuel first, and then use your outer tank, right? So firstly finish the fuel of the inner tank, finish this fuel first finish this fuel, and then use the outer tank fuel. Similarly for this thing, firstly use the inner tank and then use the outer tank. Why? Because the fuel that is present in the outer tanks helps to reduce the bending moment, right? So the fuel that is present in the outer tanks, they will have a larger moment again, you might know from the previous lecture, the distance multiplied by the force, right? So since they are at a very far end, so the distance will be larger, and which means what? Larger moment. So you might know that the wings of the aircraft used to bend again from first lecture, literally from the first lecture. The wing used to bend, there was stress, there was bending, right? All of the compression forces and all. Right? So if you are following the series, then you will know definitely, right? So to reduce this bending moment, we have your end tanks filled with fuel. So what will it do? It will apply a downward force or a downward movement, more precise, right? So downward movement will be applied by these tanks. So this will reduce the wing bending moment, right? So that is why your outer tanks are emptied at last, right? So the sequence is center tank first, right? So center tank first, then use your inner tanks as number two, and then use your outer tank as number three. Then we have fuel jettison or fuel dumping. All right, so what is fuel dumping and jettison? You might have seen your aircraft literally throwing off fuel. So they are literally flexing by throwing off fuel, right? That we have plenty of fuel. So it is done only in the case of emergencies, right? So what happens if an aircraft takes off from a runway, right? And right after takeoff, it has to return for landing because of some critical failure, right? So the aircraft that took off is very, very heavy, right? So it cannot land with that heavy, land that very heavy aircraft, right? So they have to hold and they have to dump the fuel, right? So they have to hold and jettison the fuel so that they can make the aircraft lighter and they can come for landing when the aircraft is light enough for landing, right? So it is required an aircraft whose maximum landing mass is significantly lower than the maximum takeoff mass, right? So if the aircraft took off and the maximum takeoff mass is okay, but the landing mass is very, very low, right? So the aircraft cannot land with this heavy aircraft, right? So they'll have to hold, and then when they are light enough by jettisoning the fuel, they can land the aircraft, right? This is fuel jettisoning, also known as fuel dumping. Right, then there is fuel quantity measurement, right? It's very important to know how much fuel you have in your engine, sorry, in your fuel tanks, right? So the quantity measurement can be done in two methods. You can either measure the volume of the fuel or you can measure the mass of the fuel, right? So in light aircraft, you rely on measuring the fuel volume, right? And in larger aircraft, you measure fuel's mass because the mass becomes very, very important for performance calculations, right? How much runway you need, what is the weather condition like, how much lift force will be there, how much weight will be there. So for all of those calculations, you need to measure mass, and that is why in your large modern aircraft, we use what? Mass measurement. For lighter aircraft, we use volume measurement. Now, measuring the fuel volume, right, in the light aircraft system. So, we measure the volume with the help of a float and a variable resistance. So, this is a very, very simple system. You have your fuel here filled with fuel, right, and you have a float switch here. So, you might have seen these kind of switches. They are literally just floating over the surface, right? So, they are a ball kind of switch and they are floating over the surface, right? So, they are connected with a variable resistor. So this gray color thing that you're seeing over here is a variable resistor. So if you have taken physics in your 12th, I guess, so there will be these kind of some kind of experiment or practical they do. So you might know that what a variable resistance is, right? So if you move this arrow around, if you move this left and right, then your ammeter reading will change. So this is an ammeter, like this is the instrument that you have in cockpit is actually an ammeter, right? So what ammeter does, it measures current, right? But you have calibrated the ammeter as such, it will indicate the fuel quantity, right? So calibrated in that way, but it is actually an ammeter which is measuring the amount of current, right? So this is a variable resistor, and your this thing is moving, your float is moving the left and right, and this is causing the reading on your ammeter to change, right? So this is a very, very simple method that you use in your light aircraft for measuring the fuel volume, right? and it has some disadvantage. What are the disadvantage? As the attitude of the aircraft changes, the fuel indication changes. Right, in this diagram you can see that the aircraft, for example, it is in like this kind of attitude. The aircraft is in like climbing kind of attitude, right? The nose is up, so this has caused what the fuel to literally like go backwards, right? So this has caused the fuel to move because the float switches are dependent on the fuel level. So the float will move and this will cause your fuel indication to change, right? So this is an issue, right? The fuel actually hasn't changed the quantity volume wise, but it is showing a change in the volume. And the second issue is that does not compensate for specific gravity changes, right? So you know what a specific gravity is, and it can change with temperature, but there is no such system in this kind of fuel measurement device that measures the change in specific gravity. All right. Then there is measuring fuel mass, which you use in your larger aircraft, and it uses capacitors. Right, the fuel mass is determined by using capacitors, so you don't have to go in any details about these kind of systems. They basically use a capacitor, and you might know that capacitors they need a dielectric, right? So if you don't know what a dielectric is, leave it, right? So dielectric is your fuel in this case, right? So you're using your fuel as a dielectric, and your capacitor. So basically, you just need to remember that they use what capacitor type of fuel measuring device, which measures the mass of the fuel, right? And the property of dielectric changes as the specific gravity changes, and hence it accounts for the change in specific gravity, right? So this is the advantage as compared to a previous system which was not able to detect change in specific gravity. These kind of capacitor based system will be able to determine if there is any change in specific gravity, because the property of the dielectric itself, the property of the fuel itself changes, which changes the capacitance, and hence it will be shown on your uh, meters, right? And also by use of capacitors in pair, the volume change due to attitude can be rectified, right? So the second problem that we had was due to the aircraft was having a like nose up attitude, then the fuel was sludging backward. In the second image you can see that the fuel is actually sludging backwards, right? But because you have used multiple capacitors, 1, 2, 3, and 4, so because of these multiple capacitors you have solved this issue of uh, fuel quantity change due to change in attitude, right? So you have solved both the problems and you have measured the mass using capacitors. Then there is a little bit about refueling. So whenever you are refueling the aircraft, it is a regulatory requirement that the APU should be not turned on or off, right? So it is okay if you have your APU running, it is fine. It is also okay if you have your APU off, right? So on and off is fine, but during refueling it is not allowed, right? So whenever you are refueling the aircraft, then in that particular moment you cannot turn on or turn off the APU, right? But if you have your APU on, then you can refuel. If you have it off, then you can refuel. But during the refueling process, you should not switch on or off, right? So this is a regulatory requirement. Remember, this is again very, very important for the exam. And before refueling the aircraft, it should be bonded with the fueling equipment, right? So as you can see, this is a wire which is connecting your aircraft to the fueling vehicle. So this is a conductive wire, and it helps to reduce any potential difference if there is any, right? So for example, a very lame example that, for example, this is at 5 volt and this is at 4 volt, right? Due to any reason, right? So there will be a flow from high to low, high potential to low. So this will be a flow, and this flow of electrons will be known as what? Current, right? So this, to avoid this, you firstly connect it with a wire, and you make sure ki acha, if there is any potential difference, then it will neutralize, because connecting the wires will neutralize it, right? And so there is no chance of sparks or anything, right? So this is using wires so that no potential difference between the equipments of the aircraft, right? Equipments in the aircraft. So that is it for your fuel system, and in total your aircraft systems And guys, if you have actually watched the series completely and you have liked the series, do let me know in the comments. I never asked you to comment, like, or subscribe, but this is the end, and I really would appreciate if you would do a little subscribe and a little bit of thumbs up. That would be very, very appreciated, right? And again, a little promotion. So you can join the live classes. The links are in the description, and you can just click on the Google form that I have attached in the description. Just click on that, and I'll see you there. We'll connect. We'll see how it goes. All right. Bye bye. Ta-da. Enjoy. This was the last video of the series, by the way.